Hello, everybody, and welcome to the Smoko podcast. My name is Alexis Armstrong, your host. Nice to meet you. The Smoko podcast is a place to celebrate and highlight women, trans women, and non-binary folk working within STEM and trade occupations. So please tune in, join us, take a break. We're on Smoko. Today, we're extremely lucky to be joined by the lovely Dr. Samantha Bova. Dr. Bova, Sam, she's an assistant professor at the College of Earth and Environmental Science at San Diego State University. Her area of expertise is looking at marine geology and paleoceanography. So she's a climate scientist. Her work is specializing in reconstructing past changes in Earth's climate, and this is using marine sediment and geochemistry. So we're going to talk all things geoscience, her experience as a professor. We're also going to talk a little bit about her research because she researches something really cool called the Holocene Warming Conundrum. So we're going to talk a little bit about that and just her experience within geoscience. And Dr. Bova, Sam, it is so nice to see you. Thank you so much for coming onto the show.
Sure, it's great to be here. Thanks for inviting me.
Oh, you're welcome. I'm so excited to talk about it. Me and Sam, we've known each other. We've sailed a couple times together, and it's always just an honor to talk with you and to have you on the show. I said before we were just catching up that Sam's a freaking badass. So it's going to be a good episode, I think. I really do. And to maybe get us started and to talk a little bit more about you could you walk through how you became involved with geosciences? Because I know that I ask this question to almost every single one of my guests. It's a little bit repetitive, but I'm always really interested in how women found these fields and occupations because they're not really marketed to us. So how did you go from collecting seashells at the beach to then being like leading an oceanographic cruise?
I think a lot of it started just when I was young, having that kind of innate curiosity about the world around me, and especially the natural world. And I think that is in a lot of us as kids. Sometimes it fades a little bit. I was fortunate to have a geo-environmental science class
Wow.
in my high school experience, which is not the case for a lot of
Yeah.
the country. And so that really rekindled this love of looking for seashells and rocks in the backyard and connecting it more to real world problems. So for me, it was that really crystallized connecting the things I inherently really loved to also more of an application. And so I was one of these students, a rare breed that applies to university wanting to be a geologist. I definitely credit a lot to having that opportunity in high school. I do see more of those classes coming to high school level now, which I think is really encouraging, but that was formative for me. Once I was in university, a lot of it was people and these kind of formative experiences that I have along the way. The classes, I enjoyed the classes, but I think what really put me on this path to oceanography was my senior research experience.
Very cool.
Um,
Okay.
yeah, I never took an oceanography class. I'm not even sure I took a climate class when I was in
That's wild.
undergrad.
Yeah,
Yeah.
your life. That's crazy. Okay.
Yeah, I had a great department, but those just weren't the strong suits. My senior thesis, I was looking at these calcium carbonate deposits. They
Oh,
form in
love it.
freshwater systems. So not quite in the marine realm yet, but we were trying to think about getting clues about past climate from these deposits. Long story short, we weren't able to do that from these
Mm.
deposits. And even if we were, they would have provided just these like snapshots
Yeah, they're
of
too little. Yes. One like
exactly.
specific thing in that one area, they weren't like well known enough, but still
Yeah,
cool.
it was still cool, but I was like, you know what? I would really like to go somewhere, like work in a system where I can, look at continuous records of climate going further back in
Mm.
time, not just these kind of snapshots. My advisors there helped me figure out that the ocean is one of the best places to do that. So I applied for grad school at that point to go into this marine geology, paleoceanography field without any background in climate.
Paleoceanography.
And thankfully, I was fortunate enough to get accepted, and I just really fell in love with it, which was really awesome. And then going to sea, I got the opportunity the summer after my first year of graduate school. It was one of these things where people had a cruise, they needed help on board, so you just
Mm.
needed students to volunteer. And so I was kind of like, pick me, sure, I'm happy to do
Yeah.
that. It was just that first time out on the ocean. It's just an experience that You know this
Yeah, it stays with
very
you.
well.
Yeah, it's like it's a very beautiful like moment that you're like, wow, I was chosen. I can't believe this is a job. I can't believe I'm getting paid. This is just
Exactly. It's just one of those, I loved being out there, being on the ocean, not seeing land for days. It felt very like the unknown and
yeah.
exploring new things. You never really know what you're going to get. That was the moment where I was like, this is what I want and this is what I want to do. And so
Very
from there,
cool.
I just took every opportunity of going to sea, I snatched it.
I love that you're like anyone that needs someone to go on board, it's me. I am gonna sail as
Yep.
much as freaking possible. I love that answer for so many things. One, I love that you had that ability to go into those courses in early education or in high school education. Because you're right,
Yep.
that doesn't happen that often. I didn't know what geology was until my second year university. And I had no idea. We didn't really have it in my school. It wasn't really something that we were even taught. So that's wonderful that you had that like funnel early on and you went
Yep.
into school being like, okay, I'm going to be a geologist. Funny how you ended up jumping really into paleoceanography with 2 feet before you had even really done it before.
Yep.
And then that experience, I think you summed it up, is like when you go on board a research vessel for the first time or you go sailing, there's something that's really romantic about it because no one's seen those rocks ever. They've never come up
Yep.
to the surface of the world before. You have no idea what you're going to get. You kind of feel
Hmm.
like you're like Pirates of the Caribbean, basically, because you're just like
Yep.
sailing on the high seas. It's a pretty almost addictive experience, right? Like
Yeah.
you get hooked for sure.
Absolutely. Yeah.
Yeah.
And it's just one of those things you're like, who else gets to do this, right?
Yeah.
And it just makes me feel really lucky to be there. I know we all work hard to get there,
Mhm.
but it's just a moment of awe, I think.
I couldn't agree more. I think it's a moment of gratitude. I think you all of a sudden you're in a bigger environment, bigger than you. And so there's like an awe, there's a gratitude there. There's just something that's really cool about it. Before we jump into that, because we are going to talk a lot about
Mm.
your research and about your time sailing. But before we go, you're an assistant professor at the College of Earth and Environmental Science at San Diego State University. Congratulations on becoming an assistant professor. It's a huge deal. Could you describe your experience of teaching and what has been your favorite aspect of teaching so far?
I'm still a pretty new professor. I just finished this week my second year of teaching.
Amazing. That's fantastic.
So that's exciting. Teaching, I would say it's really rewarding and it's also really challenging in part. But we, as folks who get hired into these positions, in most cases, we have almost no training in terms of being an educator.
Yeah, that's true. Yeah.
I would say it's pretty intimidating, at least for me at the beginning, to kind of jump into this position. I've sat in a million classrooms
Hmm.
throughout my career, but to be on the other side of that is definitely something that it feels, you're there and you're teaching these students, it feels important and you want to do it
Yeah.
really well. And then it's also a struggle because you don't have a lot of this kind of training to fall back on. But I think it's been going pretty well.
Yeah.
Once you get your feet wet, the momentum of the experience propels you
Hmm.
forward. And just being in the classroom with students and engaging with them. And I'm teaching them stuff that I, for the most part, really love and
Yeah.
get very excited to talk about. It's almost scarier before you get in and actually start doing it.
I could imagine that. Yes. Yeah.
Yeah, for me, it has been a challenge, but it has been really rewarding. And I would say probably my favorite aspects of teaching, and I haven't been doing this very long, but I recently ran into some of my students that I taught last year, and
Mhm.
they've moved on into various positions that are relevant to some of the stuff that we talked
Yeah.
about in class. It's really nice to hear from them and talk to them about how some of what we discussed in class has been useful for them.
That's
So that
beautiful.
feels really good.
I could imagine, especially when you're nervous to be like, frick, am I doing a good enough job? Are they getting enough out of their education? And then seeing it,
Exactly.
yeah, seeing them actually being able to apply it and to use their knowledge is probably really fulfilling as a teacher.
Yeah, that makes it yeah, definitely makes it feel good. The work that I'm putting into it paying off. And then I think one of the other things I really like about teaching is, like we were talking about before, a lot of students don't have geology in their
Hmm.
curriculum. I teach a class on climate change that kind of brings in a lot of students from different majors.
Oh, cool.
And I, of course, I make them learn a little geology in this class because a lot of them are very familiar with climate change impacts, but I find that very few students have this perspective that geology gives you of, you see in the news all the time, like this is unprecedented. We know that, of course, because we're comparing this to the
Past Earth.
geologic record.
Yeah.
I would say for the most, with some exceptions, that kind of long-term perspective of that the Earth's climate has changed before and it's changed dramatically, and that we can use these time intervals in Earth history to give us some context. There are definitely some students where that really, I think, blows their mind a little bit. I think giving that perspective to, regardless of what they go on to do, right? I have students in there in business and political science, and some are environmental scientists. I think having that perspective is really valuable. So
I mean, you're preaching to another geologist who's like, yes, of course it is. Everyone needs to understand the concept of geologic time. It's one of the most fundamental things in science. But I couldn't agree more with you. I think you do need to have that holistic long-term view when we think about climate. And I don't think that's been properly explained to people. I think unless you're in geology. I also think that you're doing the good work of geology professors for all of time, which is stealing their students from other majors. I mean, no one knows what geology is until you take one of these courses and you're like, hi, welcome to the department. Come join. So I think like you're kind of passing that down.
Aspect,
yeah. It's how geologists are made, really, is you take one of these courses and you switch your major.
Definitely. Yep.
Speaking of my personal experience, I would counter it with, I bet you're doing a fantastic job. The professors that I loved the most in my education were the professors that were the most into it. I don't even remember what we learned. I just remembered that professor thought it was the coolest thing that they have ever heard. And they would just nerd out about it for hours. And like that passion and excitement was what made me interested in it. That's half the battle of just getting people interested in and showing up for class and excited for class. So I feel like you're doing a great job. I know it.
Well, I'll ask my students.
I think it's true. I really do. Thank you so much for going into teaching, because I know it's something new for you, but it's an amazing thing to be an assistant professor. And it's really cool to hear that side of STEM. And I know something with your students and with your teaching is you do also a fair bit of community science education. I think that this is probably that class that you were talking about, that interdisciplinary class with the climate solutions course. You have students that work with local organizations in San Diego to develop climate solutions. I know you've also done work with like early science, K-12 education, and doing early education in geology. Could you walk through your experience of this, and then the importance of community science education and engagement?
I'll start with the importance of it. I think it's really important for us as scientists to engage with the community. The typical form of communication for academics is papers. There is no way that the vast majority of the public is going to read your papers. In fact, half your colleagues probably aren't either. Yeah. It's an important, but it's a pretty limited scope in terms of the audience that's actually going to read them. Maybe occasionally the press will pick up one of your papers and help you communicate that out, but that's pretty few and far between. The stuff that we're working on, the results, are things that in many cases are of interest, or at least should be of interest, to your typical everyday people. And especially in kind of these subjects have reached kind of some level of controversy or questioning in terms of the science. Climate change is one good example where I think the communicator really matters, and people hearing from the scientists who are actually engaged in the results and research that is showing that climate change is here and impacting all of us, and this is how we know that, can really lend a lot of trust and a greater understanding of what actually goes into science. How do we actually reach these conclusions? The rigors of the scientific method. I teach. I will teach to the second graders that I've done in like my K-12 education. Yeah. It's so valuable because this is how we figure things out. This is how we limit bias. All these really important components. So I think it's really important. So it's something that I've tried to prioritize throughout my career in different venues at different stages. My experience with kind of community outreach, one of the ones that is near and dear to my heart is working with kids. I've taken a little bit of a pause right now, but in graduate school and then as well during my postdoc, I went into second grade classrooms and delivered a science lesson for the week. So now as a postdoc, I went in every week to this classroom. We did a lot of geology stuff, but I didn't limit it to that. I promised I talked about other science as well. But I think it's the kids are, again, they're at that age where they're naturally curious about everything, pretty much,
Yeah.
including the kind of physical world in which they're living. Especially in the elementary school classroom, many teachers are amazing, but most are not science, do not have a science background.
Yeah.
And so even at the elementary school level, delivering exciting and engaging science curriculum can be a challenge, especially with limited resources. And so what we're trying to do when we go into these classrooms is just do something hands-on, really get the
Fun.
kids
Yeah.
really engaged and
Yeah.
fun, and to keep that natural, excited curiosity alive. And I think the other thing that's really great about doing this is also the stereotype is changing, but
Hmm.
there's still this picture scientist,
It's a
right?
boy. Yeah.
It's a boy in a
Hmm.
lab coat. And I think it is helpful to have women and other folks from other underrepresented groups going into these classrooms and showing the kids, like,
By
I am a
proxy.
scientist.
This is what a scientist looks
Yeah.
like. You might be a little bit surprised, but this is it.
Yes,
Yeah.
exactly. I have found that really, really rewarding. And they just get really excited to have a scientist come into their classroom who's answering their questions,
Oh,
getting like pumped up with them about doing science. Ultimately, I hope will help
oh,
have
completely.
more scientists and people
Yes.
coming in the pipeline. And then I've been particularly excited. So this past fall, I experimented with my climate solutions class about they do a final project where they're trying to investigate any form of a climate solution that they
Hmm.
would like to see implemented. My first year, we did this as a very broad,
Thought
just very,
exercise or something.
just kind of
Yes.
an
Yeah.
exercise. And the students liked it, but it still, I think, felt not tangible, especially as the students are getting very depressed about climate change,
Because
you
it
know?
seems like it's like a losing battle that, like, why even try? It seems so big and
Yeah,
scary.
it's scary for them. They feel like oftentimes that they can't do anything about it.
Yeah.
And so that's what I also really liked about working locally is that they could come up with climate solutions that could actually be implemented,
That
where they
feels
could
so
actually
good.
see an
Yeah.
impact. We worked with kind of an organization on campus, Sage, and they connected us with a local organization. So we worked with the San Diego Urban Sustainability Coalition and developed climate solutions for an underserved part of San Diego that's both climate and hopefully will impact people's lives for the
Oh,
better.
that's so
So,
beautiful. Good
and it
job.
was, thanks. I think the students, I hope the community members as well got a lot out of it. Because again, it's something tangible they could see in their city. These are not huge solutions that are going to completely
It doesn't
change it,
matter. It
but
changes a
it's,
local community. That's still
yeah,
impact. That's still fantastic. Yeah.
I definitely give a lot of credit for Sage, this on campus program. I think it's really innovative and helping faculty to
Hmm.
connect to local groups. I'm hoping to continue doing that kind of outreach as well into the future. It was really rewarding for me, but
Mm.
also for the students, and can help us connect better to the city that we're located
Oh,
in.
that's so amazing. One thing that I'll start with is probably early education so I don't forget it. I do think that science needs not a rebrand, but we just need to be better at communicating and breaking it down. Any type of community organization and involvement in science education is just so important. And in terms of representation and having a young woman scientist walk into a classroom, I think that is going to have huge impact for these young girls and boys who are there first getting to experience science and also engaging into that natural curiosity. I love that you're harnessing that and making it fun and tangible. And then your work that you're doing in the local community. What's really cool about that is this might be the second falling of science in terms of speaking to the public is sometimes it's just something that's a thought exercise or it's a theory. It's very theoretical. It's hard to pin down. It's hard to actually put into practice, or you feel like it's not tangible. To have your students take the scientific method, take everything that they're learning and actually use it and help people and seeing the impact and the good that it can bring, that's extremely powerful for every.
Thanks. Yeah, I'll just add, it also is good for the scientists, for me
Mhm.
too. It helps me get better at communicating, telling my parents what I actually do. And it's also, it's especially like the kids. It also reminds you like why you got into it, because there's definitely days where you're tired, the
It's
data's
hard.
not, it's
Yeah.
confusing, you can't figure it out. And then there's this kind of like pop of enthusiasm from the
Mhm.
kids, and it helps bring you back and remind you it reminds
Why?
me like why I love it.
It recenters you. I think of like, why do you
Yeah.
love it, but also why is it important? Science is hard, and sometimes we don't really know what's going on. And like you said, sometimes the data doesn't make any sense. I think that's also something that's really important is trying to get that scientific method. It helps with conspiracy theories sometimes too, because they're like one scientist disagrees, and you're like, of course, a scientist disagrees. Their job is to disagree. We're all supposed to disagree. That's how we move
Yeah,
the needle forward. That's a
exactly.
crucial part of the scientific method, right? That's not a bad
Yep.
thing. That doesn't mean that
Yep.
you throw out everything that you've discovered. He's doing
Yep.
his job saying, hey, I don't believe like data point number two. You're like, thank you.
Yeah.
Data point number two is correct, but thank you.
We all have a healthy amount of skepticism.
To dive into the scientific method and also what you're working on with climate change, could you speak to the Holocene Warming Conundrum? Because it's really cool. Could you explain what it is and what is this theory or this conundrum?
It's a conundrum that has been taking over my life in the last few years. So it's a term that was coined back in 2014, and it essentially refers to this mismatch between basically the mean annual temperature history of
Mm.
the Holocene, so about the last 10,000 years of Earth history, from climate models versus what our geologic proxy data are telling us. Our proxies are essentially indicators of past changes in the climate. In this case, we'd be thinking about temperature that get preserved in the geologic record. So we can analyze those today and figure out how global temperature changed in the past. From these records, essentially, they tell us that on average, and we take these records from all over the world, hundreds of scientists have made these records of past temperature. And then now there's enough of them that we can take them, average them together, and see what's the baseline, what the average global temperature has been doing. And so these data tell us that on average, the globe was warmer at about 6,000 years ago than it was in the pre-industrial period. So that suggests that temperature was warmer about 6,000 years ago and then cooled towards the Industrial Revolution. And then, of course, temperature spiked up. But our climate models that simulate climate over this time interval give us a very different picture. And they suggest that prior to the Industrial Revolution, over the last 10,000 years, the global temperature has been steadily increasing. So there was no early warm interval and then cooling afterwards. It's just been steady warming across this time interval. So this mismatch is a challenge for a number of reasons. We want to know what's going on in this time interval because it's the period that is right before the Industrial Revolution. It provides context, a baseline.
Our modern day system before humans.
Exactly,
yes.
Exactly. The mismatch basically tells us that the proxies are showing this cooling over the last 6,000 years while the models are warming. And this kind of challenges whether or not these climate models are simulating the climate system accurately. These are the same models that we use to kind of project into the future, and they're not matching the data. So that seems problematic. The heart of this temperature conundrum, though, is really if the proxies are right. So if we had this warm interval and then cooling, it's really hard to reconcile because during this time interval, we have a slight increase in CO2, nothing like what we've seen since the Industrial Revolution. So on the order of 20 ppm of CO2 versus almost 150 since the Industrial Revolution. So very small, but still significant. At the beginning of the Holocene, we had ice sheets still from the last glacial period. And these have a really important impact on the climate system because they're bright, white, shiny stuff that reflect light back to space. So having ice there can actually help cool the planet. And then in the second half of the Holocene, that ice melted. And so we no longer had this bright, white, shiny stuff to reflect light.
It to warm. Yes, exactly.
And we should be warming more heat. It's really, the question is, how on Earth would we get cooling when we have our ice sheets retreating and we have increasing greenhouse gases? These are really fundamental questions about the climate system. And they are relevant for, was there a period in the last 10,000 years that was close to the temperature that we're experiencing today? Or has it been warming this whole time and there's nothing like that? Our post-industrial warming would have been warming from the warmest temperatures of the last 10,000 years. There's this important mismatch. I'm certainly not the only person working on this challenge. What my research suggests is that essentially the climate models are right, and our proxies, they're not reflecting what we think they are.
Mm.
Our research suggests that these proxies are actually recording the evolution of summer temperatures rather than the evolution of the mean annual temperatures. And so then when we compare them to the model, we're comparing
A
apples
hot,
to oranges.
yeah, a hot
Yeah.
summer's day into a day in November.
Yeah. There's nothing wrong with our proxy.
Hmm.
There's nothing wrong with our climate models. I think what we're interpreting the data have been slightly doing that slightly incorrectly in the past. And under this interpretation, you can actually completely reconcile the proxy data with the models, and they will line up really nicely, which is quite satisfying. I will
Yes.
say it's still controversial. Not everyone agrees with me, just like we were talking about,
Yeah.
right? And that's how the field will move forward. We've suggested that the proxies are summer temperatures, not mean
Hmm.
annual. And now there's a lot more work going on to test this idea.
I have a couple just clarifying questions, maybe. One, because what is, if people aren't in this field or in geology, when you talk about the climate models, what data is that based on? Is that on what's the data set there? Because we're looking at geochemical markers and proxies when we look at the average baseline temperatures that are completely
Mhm.
out of whack with our model. But what's our model based on?
I mean, our models are based on the physics of the climate system. Essentially, we take basically the physics of radiative forcing and how that energy moves through the climate system. They're both coming at this problem of climate in completely different approaches. And our climate models, they are extremely sophisticated at this point. And I will say here, I am not personally a climate modeler. This is one of the
With
fun
them.
things
Yeah,
about
you,
science, that you
yes.
get to work with other experts that do
Yeah.
this. So they're basically looking at how the physics of how the climate system responds to changes in greenhouse gases or changes in solar radiation, that
Hmm.
kind of thing. And then letting that play out in the climate system, and then we're observing the response.
They're looking basically at the physics or the structure of climate, our planet, kind of Earth history of our planet's movement in relation
Mm-hmm.
to the sun, in relation to greenhouse gases. And so they're doing that model based on physics. In a geoscience perspective, we're looking at the geochemical markers trapped in marine sediment all around the world. And we're
Yep.
using all of those markers within this time period to do an average baseline calculation. Could you maybe explain a little bit more the role of seasonality? Could you talk about how you estimate seasonality in your data sets?
In the models, we would expect warming because of retreating ice sheets and rising greenhouse gases in the Holocene. But the arguments that you might not get that is that the climate system is extremely complicated. And sometimes things respond in nonlinear ways. You don't necessarily have
What
the
you
ice
see here.
sheet
Yeah.
retreats and then you have this clear increase in warming because the ice sheets are retreating. And then you also have changes in vegetation, which
Hmm.
impact the landscape. It's a very complex system, which is why we have to use climate models because we can't do these calculations by huge amounts of computational power to do this. So I will say that it's possible, but it's not in the current state of the art climate models that we don't see these strong nonlinear feedbacks. But I would say that's the counter argument is that maybe we're missing some
Something from the model.
feedback
Yes.
in the
Yeah.
model that might not be there. And so on seasonality, a lot of our proxies, we're actually looking at the remains of organisms. In the ocean, oftentimes we're looking at the kind of remains of plankton that live. These guys live a couple weeks out of the year. The chemistry of their shell or molecules that they create are going to give you this kind of snapshot
Yeah.
of what climate was during their lifespan. And many of our proxies are like this. For a long time, we have just assumed that they're mean annual, that on average, the shells that accumulate at the bottom of the ocean will generally reflect all times of year. But we know that this isn't necessarily true in the modern. Now that we have satellite data from space looking at plankton bloom, you
Yeah,
can see
it's true. You
that
can see
doesn't
how
always
big.
happen.
Yeah.
Yeah, so like they happen in these events. These organisms are responding to their environment. When things are good, they're gonna reproduce. And so it's not crazy to think that the records that we get from these organisms that get preserved in the rock record and the sediment record could be biased to a time when they were happiest, when they had
Mm.
all the stuff that they needed. But it's been a challenge is figuring out when that time period was. It's really hard to know today, looking at just the shells that accumulate in our sediment core that we can look at. It's not clear necessarily what time of year that those organisms were living or what what 2-week period each of the shells are recording. So that's something that has been really challenging. There's different ways that people have tried to approach doing this. One of them is looking in the modern and saying, this organism that was living 10,000 years ago, it exists today, and today at this location, it blooms during this. And then you might be able to take that from the modern and then apply it to the past. And a lot of folks have done that. The challenge is because of how Earth orbits the sun and our current configuration, the magnitude of the difference between our seasons today is actually at a minimum. The signal right now is really small. And it's very possible that in times in the past when our seasons were more extreme, there's a larger contrast between them, that the seasonality of these organisms might
on a magnitude
also
bigger.
be more extreme. We have our approach for doing this is to go back to a time in Earth history when seasonality was really strong, and to use these time intervals to assess whether or not the temperature record we're getting is more consistent with the climate forcing that's happening during one season or the mean annual. And
Smart.
So we basically leverage these time intervals when that signal is really big, and that we use that to help us interpret what season our proxy records are recording.
Very cool. Yes, to test them out, basically, to be like, what record are you showing us? Are you showing us seasonality, or are you showing us baseline temperature?
And I would say there's nothing wrong with seasonal records, right? If you think about our climate system today, the summer season is what drives the monsoon. Summer temperatures are what are melting our glaciers. The mean annual it's a nice benchmark to use to compare to climate models or to compare to today. But a lot of climate phenomenon are actually seasonal. They're driven by seasonal components of our climate system.
100%.
Although not everyone agrees that our approach for extracting the seasonal component of these temperature records is the right one. We're working now to improve it and get even better. If we are able to do this and convince everybody that this is working and we can actually get these distinguished between a seasonal versus a mean annual record, it gives us more information about the climate system. And it could potentially give us this information that we have really had a hard time getting. These records of seasonality have been very challenging in the past, and will help have an even better understanding of our climate system.
I agree. I don't think that we usually think about seasonality and these blooms of productivity, right? It's hard to model an ancient system to be like, what happened with seasonality? What was their life cycle like? What environment did they like? And it's hard to see that one day snapshot when we're looking at them in marine sediment. It's very hard to understand times. Any new information that we can get on seasonality, I think, will be a very powerful thing. Kudos to you figuring this out. I know it's still being debated. It's active, fresh science. It's going to be duked out in papers for a long time. Thank you for explaining it a little bit more.
Always happy to talk about it.
I know that to get this research, you do both cruises, and then it's also heavily lab-based. We met the last time that we sailed together. You were the co-chief, which is amazing. I think you were probably one of the youngest co-chiefs that we've ever had, if not the youngest. So that is a fantastic achievement. But you do these marine expeditions where you collect all of this material, and then you go back to the lab. Could you walk through each one of those? What do you like about them? Do you like lab versus cruises better? What's the favorite part of actually looking at your material and looking at your data?
I love going to sea. That initial love we talked about earlier, it is a driving force for all the reasons we talked about, right? It's beautiful. It's amazing to be out there. It's so exciting especially when I was co-chief, we had picked out these locations where we're going to get sediment cores, but then you never know exactly what you're going to get. It's very nerve-wracking, I will say, but also very exciting to actually see these things you've been planning for come into fruition. So that's really amazing. And the other amazing part of these cruises is you meet lots of amazing people like yourself, and everybody's away for 1 or 2 months. There's limited access to the outside world, for better or worse. I think overall for better.
Yes.
It's a time that you really have to completely focus on the mission. And this is something that I don't think you you get a lot when you're home, which is great. You have personal lives, you have other things going on, but it's a really unique experience to just be totally in something
Immersed.
that I don't
Yeah.
you get too many other ways. And then just being on the ship, again, immersed, but with all these people from all over the world, scientists who we're all there because we're interested in the material we're getting, but it's
Mhm.
often from really different perspectives. And so it's just an amazing learning experience from other people who are out there. You make friends that really for
Yeah.
life in many cases,
Yeah.
that environment can be really amazing. So yeah, I love the true love is going into the field. We get a lot of information when we're at sea, but most of my work we have to bring the cores back, sample them, and bring them into the lab to do the final analysis to get our sea surface temperatures that help us think about global temperature change and other kind of components of the climate system we're interested in. And so there's still discovery that happens years after these
Oh,
expeditions
100%.
happen.
Yeah. I think one problem with it being immersed is that you have no free time. Of course, it's going to
Yes,
take years to unpack all of the stuff that you brought home because you could barely scratch a surface, right? Like you're running around like
yeah,
a chicken with your head cut off, being like, okay, I have 200 samples to process in one day. Just put them in a baggie. We'll deal with it later. It's going to take
yes.
years to unpack that amount of material.
It's amazing how much work gets done when everyone has no or very few distractions.
Yeah.
I like both components. Now I used to do a lot of the lab work myself. Now that I'm a professor, a lot of that is actually done by my students. That's been a little bit of a transition, stepping back a little bit from every aspect of the research process. It takes a little getting used to, but overall it's good because then the lab work, I like it. I like kind of the variation in your day. Now that they do a lot of the lab work, it lets me do more of the kind of
Research and more
thinking and data
thinking.
analysis.
Yes.
But it's definitely a bit of a transition
Oh,
there.
I could only imagine, Sam. I feel like every single scientist that I've ever met, myself included, are like control freaks to an extent. I'm like, I'm sorry. I like watching someone else like pipette something. I'm like, oh, that was so disgusting. You touched the side. I hated everything that you did. Please just let me do this. Watching
Yep,
someone do
yep.
your lab, you're like, this is the seventh layer of hell in my mind. I'm like, please just leave so I can just do everything myself. I couldn't
Yep,
imagine that. And you want to be supportive. They're your students. You want to help them on their journey, help their research. But
yep.
then at the same
And
time, you're
they're great.
probably,
Yeah, and that part is fun too. And it's different teaching other people how to work in a lab and to
mm-hmm.
collect data. And when the data comes off the instrument, like I am just I am always so excited to plot it up.
Yeah.
It's still unknown, right?
Mm-hmm.
Nobody knows what that data is going to look like until it comes off.
That initial discovery in a lab, yes, it's not the same as being out in the field and having this romantic experience with all of these international people, but there is something still wonderful about it. And when you get your first
Yep.
set of data, you're like, ah, and something comes together. One thing that we haven't touched on yet is when you were co-chief, and you mentioned a little bit of all this work that goes into it, and then seeing your first drill course. How much work goes into it? Sometimes it can take like up to 12 years of sonar and all of your like geophysical stuff that has to go into it before. Like, how much time did it have for
Mm.
prep before you went out for your expedition?
So mine was a bit different. But yes, many of these expeditions, people have, yeah, a decade. It's
Mm.
not completely out of the question in terms of the amount of years people put into planning these expeditions. I was pretty fortunate. The expedition that I led was organized differently, and the timeline was a lot faster. We wrote the proposal and we were at sea, I think, within 2 years.
Whoa.
So that was really fast.
Yes.
But that is unusual. And in part, it's because of the nature of the expedition. We weren't drilling as deep. So the requirements for site characterization that we were pouring into were not as stringent. For our expedition, I give a lot of credit to colleagues in the field who readily shared data so that this
Oh, same.
expedition could
Yeah.
happen. In general, our field is pretty collaborative because it takes a
You have
lot
to be.
to put
Yeah.
these expeditions together. Yeah, exactly. We were able to folks shared data that were able to give us the information we needed to identify locations. I would say things that surprised me about doing it's the science. I knew that was there,
Mm.
picking the right sites, having the science justification and plan for what we are going to do with them. But there's a whole other side of it, which is logistics.
shipping and getting people down to Chile and to Patagonia. Yes.
And
Yeah.
especially when it gets canceled and rescheduled.
Yes,
So
it
you do
did.
all of those
Yeah.
things
I
twice.
forgot about that. It
Um,
did get rescheduled multiple
um,
times. Yeah.
yeah, I don't think I was fully prepared for. And a lot of it was taken care of by the International Ocean Discovery Program and the
Mhm.
folks operating the vessel. So I didn't even do all of it. I still felt like a travel agent for half the time. I was like identifying people. We took a lot of students. That was something that was formative for my career, and I wanted to give this opportunity to other students to sail. So our expedition was dominantly students, and that was one of the goals was to give that experience to young scientists. But identifying all of those students who are going to apply, getting them their flights and hotels, and
Herding
then
cats.
so there's that aspect of it that was surprising. Permitting was also something I
Mm.
knew about, but I've never been. So we were drilling in the coastal waters of Chile, so we had to have permission from the government to take those samples, which is totally reasonable. But I was getting emails from the State Department who was communicating with Chile, which is just a situation I never expected myself to be in. There's a kind of always a surprising amount of work that came from other components. 100% worth it. I'm so happy that I had that opportunity, and it was hugely important for my career and development.
I can't believe it. Again, I think you are like the youngest co-chief or one of the youngest co-chief, and it's a huge honor. It's amazing. You deserve it. It was a fantastic expedition. I think that we did really good science. I love that it was a lot of young scientists and students that got to come on the JR for the first time and have their first marine expedition. I think that's a fantastic kind of formative experience, like you've said. We'd been in it or had done so many expeditions. You're still blown away sometimes by the amount of logistical work that needs to go into it and by the amount of things that could go wrong. Like sometimes you are just on the edge of your seat to be like, today are we going to get the email from Chile? Okay, then we can go. If not, we're going to have to go like completely at
Yeah,
another location or just sit here for a week until we get that go ahead until someone allows us to do something. So you still, even if you can be in this industry for 10 years, you're
yep.
still shocked by it.
I got that
Yeah.
email from Chile when I was getting on the flight to fly down. So,
Yeah.
yeah.
So different. I remember there was one, we were just hanging out in off the coast of Mozambique for a week waiting for a go ahead. And I think if
Yeah.
you looked at our track, we went in circles because we would go down and
Yeah.
be like, okay, nope, we have to go to South Africa. And then we'd get the like, oh, yep, you're cleared for Mozambique. And then we'd come all the way back.
No, it's brutal, right? Because the
Yeah.
people who are leading that have probably spent years and years putting this together, and to just be sitting there so close to your goal but not able to do anything. Thankfully that was not what happened to us. We had a couple days in port for weather, but we got quite lucky.
You nailed it. The last one to wrap us up. If you could go back in time and give yourself some advice when you were just starting, what would it be?
It's a hard one. I think for me, there's all these junctures in your
Mm.
career when you could go one of two ways, right? You have those junctures every day, but some of the real big ones was when I was in undergrad applying to grad school, where I went to grad school. And then after grad school, where I did my postdoc. Other ones in there too. For this research project, do I want to learn this skill or do something else? The moment it feels so huge.
Yeah.
And it is, right? If I
Yeah.
picked one of those other things, who knows? It could be a totally different trajectory. Things have worked out. There's no way that I pick the quote unquote right thing every single
Yeah.
time. I think in the end, it matters less about actually some of those decisions and more just like what you do with it afterwards. And so I think I would just put a little bit less stress on
Pressure.
myself in
Yes.
those
Yeah.
big ones, but also the
Yeah.
small ones of, if I make this choice, is it going to ruin everything or
Yeah.
go this
Yeah.
direction? And it's not, right? Things probably would be different, but it's not to say that it wouldn't be the same. It wouldn't have worked out just as well. Or so I think I would just tell myself to chill out a little bit. Yeah.
That's honestly wonderful advice. I think everyone probably needs to go back and tell
But
their
it's
past self to be like,
impossible, right?
calm down. It's human nature to have, I think, that idea and that stress behind like, what decision do I make? You're going to be fine either way. And it's also probably going to have less of an impact than you realize. And you can always
Yeah.
get back to maybe what you wanted if you had strayed from the path a little bit. You can
Yeah.
always find your way back or do something a little bit different. I like that idea. And I like just the idea of enjoying it and being present. And what are you going to do with this decision? Now you've made this decision. It's honestly, the other decision was good. This one's also good. But what are you going to do now?
I think in the most part, it's not as ever as consequential as it feels in the moment. And it's
Mhm.
impossible. Like I can tell myself that now, and I'll probably still behave the exact same way in the future, but maybe
It's good
over and over
advice.
again.
Dr. Bova, Sam, thank you so much for coming on today. I really appreciate it. I learned so much. Thank you for talking about your research. It was fantastic to have you on the show.
Thanks very much. It was fun to be here.
Thank you guys. Thank you for listening. This has been the Smoko podcast. Thank you very much for listening, and we will talk to you next week.